Okay, welcome back to our little discussion on waves. Just a quick refresher on the anatomy of a wave. With all the different parts of the wave, we have our rest position. The yellow dashed line is the rest position. We have the wave itself, which is the red line. We have crests, we have troughs. We have a wavelength, which is the crest to crest distance, or the distance between any like points on adjacent waves. And we have the amplitude. So the amplitude is the displacement from rest position. So for a transverse wave, that's what we have. For a longitudinal wave, remember we have compressions and rarefactions. There are no crests and troughs. Those distinguish the longitudinal wave from the transverse wave. And then finally we had our properties of period, frequency, and speed, and we had the fact that the period and the frequency are reciprocals of each other. Okay, so that's important because what we're going to talk about next is the relationship between speed, frequency, and period. Okay? So, we all know that speed is equal to d over t, right? We've been doing that since, I don't know, grade 5, grade 6, something like that. If we're going to look at a wave, we're going to look at the speed of the wave, so v is equal to d over t. Now, what property of the wave might relate to the d, the distance value? Okay? Well, we've got the wavelength, which is a measure of length, and then for t, we have the period of a wave. So a wave will travel a distance of one wavelength in a period t, so we can replace d and t with wavelength and period. Okay? So when we do that, we wind up with this equation. V is equal to lambda over t, where lambda is the wavelength and the capital T is the period. Right? And we also remember that frequency is the reciprocal. It's 1 over the period. So we can take that 1 over t and we can replace the 1 over t from the term above it with frequency, and we wind up with V is equal to F lambda. Okay? And that's what we refer to as the universal wave equation. And it's called the universal wave equation because guess what? It's universal. That holds for any wave. Okay? So let's look at an example using the universal wave equation. Sound waves, if we have a sound wave traveling at about 340 meters per second in the air, we could say what's the wavelength of the note of middle A, which has a frequency of 440 hertz. So if you played A on the trumpet, it would have that frequency of 440 hertz. So what's the wavelength? Okay. Go back to our equation. V is equal to F lambda. What are we looking for? We're looking for the wavelength, which is lambda. So we're going to rearrange our equation. Lambda is equal to V over F. And then we just have to plug in our values. So our speed, V, was 340 meters per second, and our frequency was 440 hertz, or cycles per second. And those units cancel out, and we wind up with 0.773 meters. Okay? So the wavelength of 440 hertz is 77.3 centimeters. Okay? Let's look at another example. Radio waves travel at the speed of light, where the speed of light is 3 times 10 to the 8 meters per second. Our local CBC radio station broadcasts at the frequency of 99.1 megahertz. So then the question is, what's the wavelength of that radio wave? Okay, so it's basically the same question. Lambda is equal to V over F, but in this case, V is the speed of light, right? Because radio waves travel at the speed of light, and F is our 99.1 megahertz. And when we solve for that, we get 3.027, or 3 meters and 2.7 centimeters. So that's basically 3 meter sticks plus a nubbin of chalk. And that's the wavelength of the radio waves for CBC radio. Okay? So let's try one more. I have a green laser pointer. It has a wavelength of 532 nanometers, so what's the frequency of that light? Well, again, we can use our universal wave equation, V is equal to F lambda. In this case, we're going to be looking for frequency, so we're going to rearrange to solve for frequency, so it's going to be, frequency is V over lambda. Our speed is speed of light, 3 times 10 to the 8 meters per second, and our wavelength is 532 nanometers, or 532 times 10 to the minus 9 meters. And we plug that all in, we wind up with 5.64 times 10 to the 14 hertz. So that's a pretty big number. If we want to use SI prefixes, that will come out to 564 terahertz. So that's 564 terahertz is the frequency of green light. Okay, so that's quite a bit higher in frequency than the radio station in the previous question. Okay, I know this one was short, but this is it's an important concept to get down, that this equation, V is equal to F lambda, is one of the important equations we're going to be using in physics, and you should get used to practicing with it. All right, thanks a lot.